All right, hey everybody. So welcome back to Math Background for ML. Hope you guys had a good break. So I think today we're going to start on a new topic, which is graphical models, and then we'll progress to optimization after that. So let's get started. As always, please ask questions on Piazza. So we've described a bunch of ways to model, to make models of different random variables as part of setting up a probabilistic model that we can optimize, including, for example, maximum entropy, different multivariate distributions like the Gaussian, and what I wanted to do today is talk about another perspective on how to set up a model over multiple random variables. And this perspective is often useful for sort of roughing out a model, basically thinking about the relationships among your variables in such a way that you're able to, first decide what depends on what, and then write down the precise model that that's active. So, to talk about graphical models, so first I should put a disclaimer. We're only going to say a little bit about graphical models. You could take an entire course about graphical models, and in fact, our department offers one. It's a nice course. You should take it if you're interested in it. But what we're going to do is talk about just sort of the high-level concepts in graphical models. So the first high-level concept is the idea of a direct versus an indirect interaction between variables. So graphical models are all about talking about interactions between variables. Let's say what an indirect interaction is first. So we have some set of variables, call them x, y, a whole bunch of other ones, right? So we might have, 20 different variables. And we have two variables, call them x and y, and we'll say that they interact with one another if knowing something about x tells you something about y, or vice versa. And we'll say that the interaction is indirect if you can find some set of other variables, not x and y, but call them z1 through zk, such that these variables mediate the interaction, right? So if you know just x, it tells you something about y. But if you know z1 through zk, then knowing x doesn't tell you anything more about y than what z1 through zk do. So, right, so in symbols, sorry. So in symbols we have that x is not independent of y, but that x is independent of y if you know z1 through zk. Okay, so that's this is an indirect interaction. So if there is no such z1 through zk, right? In other words, if you can't make x independent of y by conditioning on some other variables, then we'll say that it's a direct interaction. Okay, so as an example, you could imagine three variables. Whether a person is infected with the virus that causes flu, whether the person is showing symptoms of flu, and whether the person decides to stay home from work or school, right? So a reasonable model would be x and y interact directly, right? The flu virus can cause you to have symptoms of flu, and y and z interact directly. If you feel bad, you're more likely to stay home from work or school. But x and z interact only indirectly, right? So having the flu virus has no further effect on whether you stay home from work or school beyond the effect that goes through whether you feel bad or not, right? So, so that's an example of a direct versus an indirect interaction. So you can draw a graph that represents this interaction structure. So here it is at the top of section 3. So what we've done is we've drawn an edge between any pair of random variables that interact directly, right? So this is saying that x interacts directly with y interacts directly with z, but x doesn't interact directly with z because there's no edge. Now x interacts indirectly because there's a path, right? But there's no single edge that goes between x and z. Right? So you can make these graphs a lot more complicated. Here's just a slightly more complicated example where we've split the flu symptoms into headache and fever, right? And let's say that that's all of the symptoms of flu, although I know that the real flu has more symptoms than that. But you could say then that the flu virus interacts directly with whether you have a headache. It also interacts directly with whether you have a fever. And then those two things interact directly with whether you stay home. And again, there's no direct edge from flu to stays home, and there's no direct edge from headache to fever. There's headache doesn't cause fever, right, and fever doesn't cause headache. Right? So this kind of graph, this is called a Markov random field, and it's one of the most common types of graphical models. There's lots of other types. We're not going to really talk about them here, except to mention that it's a good idea to know that there are these other types. Some of the names, if you're interested in looking them up, are Bayes nets, factor graphs, and junction trees. And again, if you want to learn more about all of these different types of graphical models, take the course on graphical models. It's a nice course. So in general, a graphical model is any way of using a picture to describe properties of a probability distribution. So here, the property that we're describing is direct versus indirect interactions. Excuse me. And so the advantage of doing this sort of thing is that if you have a graphical model, you can use it to reason very simply about the properties that it represents, right? So it's very easy to look at this and decide which variables interact directly or indirectly. And so that's a that's a task that's made easier by having this picture. There's a lot of more complicated properties that you can potentially reason about using graphical models. Things like, various types of independence relationships, or being able to calculate conditional and marginal distributions. These things, again, we're not going to talk about them here except in a special case that I'll get to in a sec. But it's useful to know that there exist techniques for doing these things. All right, so graphical models are related to something that we've talked about before, which is maximum entropy distribution. So if you remember, here's the functional form of a maximum entropy distribution. And so we have the maximum entropy distribution is based on some vector of statistics t, which you evaluate based on a sample of your vector of random variables x. And so here's an example of t, right? It could be that if you had binary variables, you could have x1, x2, and x3, all those features. Let's say there are 3 binary variables, and then the product of x1 and x2, and the product of x1 and x2 and x3, right? Now, there's kind of a nice property of this particular vector of features, which is that it's sparse in the following sense. Each one of our features depends not on all of our possible random variables, but only on some subset. So for example, this first feature depends only on x1, and this last feature depends only on x2 and x3. All right? And so we'll call that the neighborhood of each feature. And we can draw a graph, if we want to, that has an edge between two variables if and only if they share a neighborhood, right? So here, x1 and x2 are in the same neighborhood, so we'll draw an edge between them. And x2 and x3 are in the same neighborhood, so we'll draw an edge between those. So we can draw that graph, and it illustrates this this sparsity structure of the Markov random field. And a very interesting property, it illustrates this sparsity structure of the maximum entropy distribution. And a very interesting property is that this graph is in fact exactly a Markov random field. In other words, in this maximum entropy distribution, it is possible to prove that two variables interact directly if and only if they appear in the same neighborhood. We're not going to prove that. It's not necessarily that hard a proof, but it would take us a little too far afield. It's potentially an interesting exercise for anybody who's interested in learning a little bit more about graphical models. All right, so we make that graph, x1, x2, x3, and that graph is in fact exactly a Markov random field. And so in a maximum entropy distribution, we can reason about what variables depend on what by using this graphical model. So that's kind of cool. Let's see. So we have a couple of questions. So the first question is to draw the graph for this given t of x. But in fact, this graph is already here. This is the graph right here later in the notes. Another one is asking when it's useful to use different types of graphical model. So that's a little bit difficult to answer precisely because I've only described one type of graphical model in any detail. But at a top level, so you remember that the point of a graphical model was to make it easier to reason about some properties of the probability distribution. And so each type of graphical model will make it easier to reason about different types of properties of the probability distribution. And so different types of graphical models are more appropriate to use depending on which properties you want to reason about. So that's one answer. A second answer is that these graphical models, they are based on graphs. And if you different types of graphical models, you'll draw a different graph to represent the same probability distribution. And so and that graph, for the same probability distribution, if you represent it using a different type of graphical model, you'd get a different graph, and that graph could be more or less complicated. And so another reason to use one type of graphical model versus another is if you happen to have a graphical model that makes it really simple and straightforward to represent the probability distribution you care about. For example, the graph could be more sparse in one representation, one type of graphical model, and more dense in another representation, and you'd want to probably pick the sparse one, all other factors being equal. Let's see, so more examples or resources to read about graphical models. Yes, I mean, so the problem is, of course, that it's a huge field, and so it's hard to give like just the right size set of resources without overwhelming you. So first, in the syllabus, I've linked a nice description of graphical models. It's a section in the Elements of Statistical Learning. The lecture notes for the course on graphical models are another good place to start. There are a bunch of textbooks as well. Not sure, actually, Okay, so I'll link this from I'll link this from the I'll link this from Piazza, but there's a nice a nice paper on a type of graphical model called a factor graph, and that is by Shishang, Loliger, and Fry. And I'm not even going to try to remember how to spell it right now. I will. I'll just post a. I'll just post a link later. So I'll just. There. Okay. So I'll just. I'll add that to Piazza in a bit after class. So there's a few more questions. Let's take a look at that. So in this graph that I'm showing, all of the edges are undirected. I would have drawn an arrow for a directed edge. Oh, interesting. So people are saying the video is frozen. Let's see if I can fix that. All right, that seems to have unfrozen the video. So hopefully that fixes it. All right, so okay, so I think that's all of the questions for now. Let's go back to looking at the notes. All right, so in general, for any maximum entropy distribution, you can write down a graphical model, and in fact, the converse is true as well. For any graphical model, there's a corresponding, at least for any Markov random field, and for all the other types of graphical model I can think of offhand, there's a corresponding maximum entropy distribution. And the graphical model will often make computation easier, but unfortunately it can still scale pretty badly. So for example, if you wanted to make a graphical model with 1 million variables in it, unless that model had a very friendly form, it could become intractable to work with it. For example, to compute conditional distributions in it. However, there's one really nice example of a graphical model, which is a Gaussian graphical model. And it shows a lot of the same issues. A lot of the, like, working with Gaussian graphical models will teach you about, a lot of the issues that come up when working with general graphical models, except that there are polytime algorithms to do almost all of the interesting things with a Gaussian graphical model. So it's much more efficient to work with. So for the next set of notes, that's what we're going to talk about. Yeah, so let's just switch to that set of notes. All right. So All right, I think the text could get a little bit bigger on that. So, all right, so if you remember the Gaussian density, right? So here's the expression for it. I'm going to assume 0 means 0 for now, and I'm going to write it in terms of the precision matrix omega, which is, if you recall, the inverse of the covariance matrix. And so here's the expression for a Gaussian density. Right, and the key part is this quadratic expression here. Right, so right, and so the Gaussians are in fact a maximum entropy distribution, and you can tell that because the only interaction between the random variable x and the parameter omega is through this linear expression here, right? And by linear, it's not linear in x, right? But it's linear in omega, and it's linear in a function of x, namely the matrix XX transpose, right? So that matches the form of an exponential family. The statistic is minus 1/2 XX transpose. Here, the normalizing constant is just collecting all of the rest of the stuff in the distribution. And if you just write out an exponential family with this normalizer and this statistic, you'll get the Gaussian distribution. So that means that Gaussian distributions, because they're maximum, that means that they correspond to Markov random fields, right? So here is the Markov random field that corresponds to a general Gaussian over 6 random variables. This is not very interesting because it says that every pair of random variables has an edge between it, meaning that every pair of random variables potentially interacts directly in a Gaussian distribution. And maybe that's not surprising because you can have your Gaussian distribution have lots and lots of shapes so that there are all sorts of correlations left and right between different variables. Right, so we have this, this dense graph, and that's for a general Gaussian distribution. But what if we constrain some of the entries of the precision matrix to be 0, right? So if you go up here, we have this linear function, which is effectively the dot product between XX transpose and the precision matrix. And if we force some of the entries of the precision matrix to be 0, that's effectively the same as dropping some of the entries of XX transpose, saying that they're no longer statistics that matter. And so what that means then is that when we drop those statistics, we can drop their neighborhoods from our Markov random field, and that means that we drop some edges, right? So in particular, if we say that the ij element of our precision matrix is 0, then we can drop xi times xj from our vector of statistics, which means that we drop the edge between I and j from our graphical model. And so we'll get a graphical model that looks more like this, right? It'll have the same set of variables, but it'll only have a subset of the possible edges. So that's a nice example of going back and forth between a maximum entropy distribution and the corresponding Markov random field, which is a question that somebody just asked on Piazza, right? And so just to say that example again, right? So the maximum entropy distribution is this one, the Gaussian, right? Expressed by this vector of statistics, basically all quadratic functions, right? All products of pairs of coordinates of x. And the corresponding parameter is the precision matrix. And if we drop some of our statistics, or equivalently force some of our precision matrix entries to be 0, we get Markov random fields of different shapes, right? So if we include all of them, right, there's a feature xi times xj for all pairs I and j. That means there's an edge from I to j for every possible value of I and j in our graph. That's a complete graph. Or if we set some to 0, then there'll be a subset of the edges. We'll have only some of the edges, and we'll have a sparse graph, sparse Markov random field that corresponds to our graphical model. All right. So, given this graphical model, what does this graphical model let us do? So the first thing that it lets us do is reason about direct and indirect dependencies between variables, right? So here, for example, here are two variables that depend directly, right? These two. And then these two depend only indirectly. They depend indirectly because there's a path between them, and they don't depend directly because there's no edge between them. Okay? So that's the first thing. The second thing we can do is we can use our graphical model to do conditioning and marginalization in our joint distribution, right? So by conditioning, I mean suppose that we find out a value for some of our random variables and want a distribution over the remaining ones. For marginalization, what that means is effectively to drop some of our random variables and ask for the distribution over the remaining ones if we ignore the ones that we dropped. And both of those are fairly simple to do in a Gaussian graphical model, and they involve calculations that depend on the sparsity structure of our graph, or equivalently on the pattern of non-zeros in our precision matrix. So let's go into a little bit more detail. So for conditioning, it's actually fairly straightforward. So to condition in a distribution, right, we have this joint distribution, and to condition, what we do is we fill in values for the random variables that we observe, the ones that we're conditioning on, and then renormalize over the remaining variables so that we get a probability distribution, a distribution that sums or integrates to 1. In this case, integrates because Gaussians are continuous. So what does that look like in terms of operations on matrices and vectors? So in particular, our Gaussian is of the form, 1 over normalizing constant times e to the minus quadratic in our random variable. And if you fix some of the variables in a quadratic, you'll still get a quadratic, right? It'll be, you could get it all the way down to linear, but in this case you won't, because every term, there's no way to get just terms that are linear. So we'll still get e to the minus quadratic in x after we fix some variables, and that means that the density after we condition is still Gaussian. And so all we need to do in order to figure out the conditional density is to figure out the parameters of that Gaussian. So let's start with a Gaussian with this precision matrix and 0 mean. It turns out that 0 mean is without loss of generality. We'll come back to that. And so here's our precision matrix. By having this as a precision matrix, I mean that we've split the precision matrix into blocks, where one block is the variables we want to leave and the other is the ones that we want to condition on. So, for example, we could have a precision matrix that looked like, right, so I think that's a valid precision matrix, and we could split it into blocks like that, right? And we could say, we'll call these variables x1, x2, and x3. And so let's say that we want to condition on everything below the line, and we want to leave everything above the line, right? So we're leaving x1 and x2, and we're conditioning on x3. And so in this plot here, right, we've split x into u and v, and we've split the precision matrix into a block A, B, B transpose, right? This has to be the transpose of that because of symmetry, and C. Right? And so if we work it out, once we have this, this decomposition of our precision matrix. Oh, somebody's asking whether a Gaussian graphical model can be disconnected. Yes, absolutely. It's perfectly fine for a graphical model to be disconnected, and that just means that there's no interaction, direct or otherwise, between the variables on one side of the partition and the variables on the other side of the partition. Okay, so back to conditioning, right? So what we want to do with conditioning is just work with our expression for the prior distribution and fill in a value for the last component of x and see what happens when we renormalize. Right? So if we break up, if we use these expressions for x and the precision, omega, then this quadratic in x, we can break it up like this. This is just expanding the square with this definition for omega. And our goal, remember, we know v. We're assuming we've filled in a value for v, and we'd like to get a normalized distribution over u. So to normalize, right, what we want to do is effectively figure out how to get the Gaussian distribution, which has this as its quadratic part, as a function of u. And so we can drop terms that don't depend on u, like the last term. And then for the remaining terms, we can complete the square, right? So we want a quadratic of the form, variable transpose precision matrix variable, or variable minus mean transpose precision matrix variable minus mean. That's the form of a Gaussian. And so if we take this, drop the constant, and complete the square, we get this expression. I'm not going to go ahead and I'm not going to derive it. It's probably better to go over that derivation yourself later and just ask questions if it isn't clear. But completing the square leaves us this plus some constants that, by which I mean terms that don't depend on u. And so here, this is a Gaussian with mean equal to the negative of this term and precision equal to a, which was one of the blocks of the precision. And so that tells us how to condition in a Gaussian graphical model. It says that we keep the block of the precision matrix that corresponds to the variables that we're keeping. So there's no change to the precision matrix. And we update the mean based on this block B. Right, so we update, we update the mean based on our existing precision matrix. And so the update is basically this form, and you can see it depends on the cross interaction B between the variable we observed and the variable we didn't. And in particular, if B is all 0, meaning that there's no interaction between U and V, right, then the new mean after we condition is going to be 0. There's going to be no effect on the mean from conditioning. And that's what we should expect when there's no interaction, that there's no update to the mean. All right. Oh, and so there is yeah. All right. So to handle, I mentioned that we could handle Gaussians that don't start with a 0 mean, and the way we do that is really simple. We subtract off the mean, so basically change variables to a new Gaussian that does have 0 mean. We do the conditioning, and then we add the mean back in, right? So we change our coordinates so that we have a 0 mean Gaussian, we do the conditioning, and then we go back to the original coordinate system. And you can turn that into equations, but it's much easier to remember that recipe than it is to remember the equations. So we can go ahead and just remember it that way. But in case you're interested in the equations, this is I've worked out what the equations are here. I should also say, so the expression that I wrote above was for conditioning on a single element of our vector of Gaussian random variables. We can condition on several at once with effectively a block version of the same formula. So if we partition our precision matrix such that there's at least there's any number of variables, one or more variables that we're keeping, and any number of variables, one or more variables that we are conditioning on. There's a block version of the formula. And here it is. It looks effectively the same as this, except that some of the vectors have been turned into matrices. All right. Oh, I should say as well that if we look at the sparsity structure, right, if we look at the picture for the graphical model, that tells us something about how the Gaussian distribution updates. In particular, when we do conditioning, we don't change the block of the precision matrix that corresponds to the variables we keep, and so that means that we introduce no additional dependencies into that block. Right. All right. So another useful way to interpret this Gaussian graphical model is using linear regression. It turns out, again, I'm not going to derive it, but it turns out that if you do linear regression, oops, there's, hi, I'm in the middle of teaching a class. Can you come back later? Okay. All right. I've learned to answer my door because occasionally people knock on it to tell me that my video isn't working, but so far, fingers crossed, it seems like it's okay right now. Let's see, so why, okay, there's a nice question on Piazza now about Gaussians and maximum entropy. So somebody's asking about why Gaussians are maximum entropy, given that a uniform distribution has the highest possible entropy of any distribution over an interval of the real line. And so that's a good question. It's actually, the answer has to do with the what we mean by a maximum entropy distribution, right? So maximum entropy means, right, if we call something a maximum entropy distribution, that means that it maximizes entropy subject to the constraint that its expected value of t of x is equal to some fixed vector t bar, right? And so depending on what statistic we use, we'll get a different distribution as the maxent distribution. And depending on what value we set the statistic to be, right, depending on what t bar is, we'll get a different distribution as our maxent distribution, right? So maxent doesn't mean maximum entropy with no other considerations. It means maximum entropy subject to a particular constraint, and that constraint is that the expected value of t of x under our distribution, under our maxent distribution, has to equal a particular vector. And so in particular, to get the uniform distribution, we want maximum entropy with no constraints. And so that would mean that our vector of statistics is just the empty vector. There's no effectively no statistic we care about, we just want the maximum entropy. To get a Gaussian distribution, we would maximize entropy subject to the constraint that the mean and variance have particular specified values, right? And so that's how both a Gaussian and a uniform distribution can be maxent. And in particular, any distribution of the exponential family form, right? So if you remember, the exponential family form is p0 of x, exp of all right. I don't understand why my there we go. All right. Just because I've studied computer science for n years doesn't mean I understand why computers behave the way they do. But all right, we have this form t of x dot theta minus g of theta, right? So we have this functional form, and any distribution of this functional form can be derived as the maximum entropy distribution for a particular set of features where we're constraining the expectation of those features. All right. So all right, so conditioning in linear regression. It turns out, we're not going to derive it, but it turns out that what I just described, the procedure I just described for figuring out the conditional distribution in a Gaussian, or in a Gaussian graphical model, is equivalent to doing linear regression from the variables you're conditioning on to the remaining variables. And again, if you're interested in that, it's actually a pretty good exercise to try and convince yourself that that's true. Basically, you wind up needing to use the formula for linear regression and the formula for a block matrix inverse to relate the expression that I gave for the conditional distribution to the expression for the coefficients of a linear regression. But at least at a top level, it sort of makes sense because we know that linear regression is the optimal thing to do when you're trying to predict a Gaussian distributed variable. Optimal in the sense of maximum likelihood. All right, so that's conditioning. Another thing that we might want to do is marginalization. Marginalization in a Gaussian graphical model is conceptually really simple. If we have a Gaussian distribution and we marginalize out some variables, the distribution of the remaining variables doesn't change, right? It's still a Gaussian distribution. And in particular, their mean doesn't change when we marginalize out some variables, and their covariance doesn't change, right? Their covariance among the variables we keep doesn't change when we drop some other variables. And so what that means is that to marginalize in a Gaussian distribution, what we do is we compute the mean and the covariance matrix, and we simply drop the elements of the mean vector that correspond to the variables we're marginalizing out, and we drop the elements of the covariance matrix that correspond to the variables we're marginalizing out. And it turns out that there are some nice block matrix formulas for doing that, and these formulas are given in the notes. It's not that interesting necessarily to derive them, or at least it's not that interesting to go through the derivation in lecture. Again, if this is if you want practice with matrix manipulation, it's a good example to try and go through. All right. So let's see. So given a particular Gaussian graphical model, those are basically the operations that you're going to be most likely to want to do. So the operations are determining which variables are directly dependent and which variables are indirectly dependent, and conditioning on some of the variables and marginalizing out some of the variables. And so all of these you can do them with fairly straightforward matrix operations. And the derivation of the precise form of the updates is basically just a bit of algebra. Another thing that you might want to do with a Gaussian graphical model is to learn the distribution from data, right? So in a Gaussian graphical model, that corresponds to learning the mean vector and the precision matrix. And the best way to do that, well, I don't know about, certainly one good way to do that is maximum likelihood. And so, again, deriving the maximum likelihood estimate is a fairly straightforward exercise in using the techniques that we've already gone through in this course, except for one wrinkle that I'll get to in a bit. So in particular, let's say first that we know the structure of the graphical model, meaning we know which edges are present in our precision matrix, or equivalently, which edges are present in our graph, or equivalently, which non-zeros are present in our precision matrix. We'd like to maximize the likelihood of a sample, right? So we have a sample from our Gaussian graphical model that's capital N different vectors x, each of which has a bunch of components, one component per dimension of our graphical model. And we would like to find the maximum likelihood mean vector and the maximum likelihood precision matrix. So the maximum likelihood mean vector does not actually depend at all on the structure. It's just the empirical mean. I'm not going to derive it. It's a fairly simple derivation. And so to make things simpler, what I'm going to do is subtract off that mean. So that means effectively I'm going to center all of our variables, and then we can focus on estimating the precision matrix, which is the interesting part. So the log likelihood then, right, it's the log of the joint probability of all of the observations given our parameter, which is the precision matrix, and just filling in the Gaussian likelihood, we get this, right, the n times the log of normalizing constant plus the sum over all examples of x transpose omega x times minus a half. And if we can split this part up into a constant plus a part that depends on our parameter omega, the precision matrix. We do that by using an identity that says that the determinant of a product is the product of the determinants, and then using identity that the log of a square root is 1/2 log of the original thing. Right. And then we can simplify this sum as a trace, right? So we can each term in this sum is a scalar, so we can wrap it in a trace without changing anything, and then we can use trace rotation to bring xx transpose together, and we can define C to be the average of xx transpose across our data, right? And so we simplify it into a linear function of the omega that we're trying to estimate, plus a concave function of the omega that we're trying to estimate. And so if we were just trying to find the unconstrained maximum likelihood estimate, we would differentiate this and set it to 0. And you guys have done a bunch of derivatives like this before in exercises, so I'll just give the answer for the derivative, right? So the derivative of the log determinant is the trace of omega inverse transpose times d omega, and the derivative of the trace is a linear function, and so the d passes straight through, and we get trace of c transpose d omega. And so if we set dl to 0, that means we have to set the coefficient of d omega to 0, which means we set omega inverse transpose equal to c transpose, right, or omega inverse equals c. So that means that the unconstrained maximum likelihood estimate for the precision matrix is the inverse of the observed covariance matrix, which is exactly what you might hope, right? The most likely value of the covariance matrix is the one that we observed in the data, and so the most likely value of the inverse covariance matrix is the inverse of the one we observed in the data. All right, so up to now, this is basically straightforward application of the techniques that we've used so far in the course, although maybe a moderately complicated one because it involves a whole bunch of matrix algebra. But now, what we would like to do is get a constrained maximum likelihood estimate instead. And what that means is we're going to constrain some of the entries of the precision matrix to 0 and ask for the most likely precision matrix under that constraint. And to do that, we need something that we haven't covered yet, which is a technique called the Lagrange Multiplier. And we'll actually talk about Lagrange multipliers in more detail in a lecture or two. But for now, I'll just tell you what the answer is. So the answer is that we'll make another matrix, call it lambda, where the ij component of lambda is 0 in positions where omega is allowed to be non-zero. and the ij component of lambda is non-zero in positions where omega is required to be 0. So in other words, the sparsity pattern of lambda is the complement of the sparsity pattern of omega. Okay, and then what we want to do is we're going to set lambda in a particular way, and the answer is going to be omega is, instead of c inverse, c plus lambda inverse. And the way we want to set lambda is to make omega have the desired sparsity structure, right? So we want to change the elements of lambda in such a way that when we add it to c and take the inverse, we get the correct zeros in omega. And to find such a lambda, we can do it by gradient descent, right? And so here I've calculated the gradient, you know, this algorithm is maybe not the fanciest or the best algorithm for this purpose, but it is a very nice algorithm in the sense that you know, it's less than half a dozen lines of MATLAB code and a similarly small number of lines of NumPy code. So this gives an example of how to do, or sorry, this gives an algorithm for how to do maximum likelihood under the constraint of having a particular structure. So this tells us how to fit a Gaussian graphical model to data. All right, so then the last thing, so far we assumed that we know the structure, right, know which elements of our Gaussian graphical model are allowed to be non-zero. But instead we might like to learn them. And this is also related to stuff that we've done before. In particular, it's related to variable selection. So I should point out, by the way, that there's a ton of methods for doing structure estimation in the graphical models, and in particular for doing structure estimation in Gaussian graphical models. But one particularly nice one is the one that we're about to describe, which is basically to say that so if you remember, right, the linear regression between one block of our Gaussian graphical model and another was related to the elements in the corresponding off-diagonal block of the precision matrix. And so what that means is that we're going to use regression to estimate something about this block. And in particular, we're going to use regression to estimate which entries of this block need to be non-zero. And we already know how to determine which entries in a regression coefficient matrix need to be non-zero. That's exactly variable selection. So what we're going to do is we're going to do regression from one block to the other and use a variable selection method. And we can actually drop in any variable selection method we want. We covered one nice one, which is called forward stage-wise regression. And so then we get a sparsity pattern, and we just plug in that sparsity pattern to the given block. And we do that for all possible blocks, right? So let's say we hold out a single variable, predict it from all of the other variables, and that gets an estimate of the block, you know, one row effectively of our precision matrix, and we do that over and over again until we get estimates of all of the rows, and that turns out to be guaranteed to work in the limit of a large enough sample size. All right, so that's Gaussian graphical models. The things to remember from this are not the specific formulas, because you can always look up and or rederive the formulas. The things to remember are that there are fairly simple algorithms for doing a bunch of different operations on a Gaussian graphical model, namely determining what variables depend directly or indirectly on one another, for conditioning on a subset of variables, and for marginalizing out a subset of variables, as well as for learning the parameters, meaning the non-zero entries of the precision matrix and the mean, and as well for learning which parameters are allowed to be non-zero. right? So these are operations all that you can do on Gaussian graphical models, and the algorithms are relatively efficient. There are equivalent operations that you can do on general Markov random fields or general other classes of graphical models, and those algorithms are more complicated and also potentially less computationally efficient. But the reason for looking at Gaussian graphical models is that they give you sort of a good understanding of the sorts of things you can do with graphical models in general, although the operations tend to be more computationally efficient in the Gaussian case. All right, so that is Gaussian graphical models. And as, let's just check for more questions. Okay, it looks like no additional questions. So let's see if we can get started on the next set of lecture notes. Yeah, actually so these are the lecture notes on preconditioning and momentum, and they're actually nice ones to cover in the context of Gaussian graphical models because they use some fairly similar concepts. All right, so if you remember, we talked earlier about how to, oh, whoops. Oh, so somebody was asking on Piazza, what is the reason for choosing this partitioning of our variables? The reason is that we have some set of variables that we want to condition on, right? So we've observed some subset of our variables, and we want to take into account that information, and that's the set of variables below the line. And then the other set of variables, these are the ones we didn't observe, and they're the ones we want to keep in our graphical model so that we can continue to reason about them. And so we divide our variables into two groups, the ones we condition on and the ones we don't, and then we do the, that's how we do the partition, and then we use that partition along with the formulas that were in the lecture notes to actually perform the conditioning. Let's see, so if we have a highly nonlinear relationship between two sets of variables, can we still use Gaussian graphical models? Well, you can always use them. It might or might not be a good idea. And often, if you have a highly nonlinear relationship between your variables, that's a good indication that Gaussians on their own might not be completely appropriate. Same thing, for example, if you're doing a linear regression, right? If there's a highly nonlinear relationship, you won't get a very accurate fit with a linear regression. Now, that being said, some of the same things that you can do for a linear regression, you can also do for Gaussian graphical models. So you could, for example, do a change of variables to try to get to something that's closer to a linear relationship. Or if there's a, like lots heavy tails or lots of outliers, you could do some kind of nonlinear transformation to try to change the marginal distributions to be closer to Gaussian. So an example might be, right, like if you have a variable that's always positive and has higher variance the larger its mean is, then you could take the log of that variable. And that would transform it so that it can be positive or negative, and it would compress larger values together, and so it might even up the variance over different values of that variable. Yeah. Cool. All right. So that's all the questions that were on Piazza. So let's just take a look now again at the next set of notes. So If you remember, right, we talked about how to sketch the contours of a Gaussian given a precision matrix. And this precision matrix P, this is the same as omega from the last set of notes. In other words, it's the precision matrix of a Gaussian, of a multivariate Gaussian. And the way we did the sketching, right, was to, the contours looked like ellipses, right? And the way we did the sketching was to take our precision matrix and factor it using the singular value decomposition, which means that we have it an orthonormal matrix U and a diagonal matrix S, and we factor the precision as US U transpose. And we do that just using some code for singular value decomposition that we find as part of a library like NumPy. And then the columns of U wind up being the axes of the ellipse, right, like this. So this is the first column of U, and this is the second column of U. And the diagonal elements here wind up being related to the spread along each axis, right, to the width of the distribution along each axis. So because this is the precision matrix that we factored, larger values in this diagonal matrix correspond to narrower values along the corresponding axis. If we had factored the covariance matrix, U would be the same, and we'd just get 1 over the corresponding diagonal elements of S. And so for the covariance matrix, larger values would correspond to wider spread. But we did the precision, so larger values correspond to narrower spread along the given axis. All right, so we covered that earlier, and I wanted to point out that in fact, it doesn't matter that it was a Gaussian, right? Anyway, any reason that we have a quadratic, we can use the same setup, the same procedure to try and sketch the contours of the quadratic. And then to get a Gaussian, right, we just take e to the minus quadratic, which is a monotone transform, and so it doesn't change the contours, it just changes the height of each contour. Right? So that means that anytime we have an arbitrary quadratic, x transpose px, or 1/2 x transpose px, we can use this same procedure to sketch its contours, meaning we factor the matrix P that defines the quadratic, and we use the factors U and S to sketch elliptical contours. All right. And if you remember, we talked about in stochastic gradient descent that the speed at which stochastic gradient descent converges depends on what we call the conditioning of our loss function. And qualitatively, well-conditioned loss functions are ones with contours that are nice and round, and poorly conditioned ones are ones with contours that are very long and skinny. And again, qualitatively, the reason that the convergence is slow in a poorly conditioned problem, right? So you'll have something that looks like this, right? So our poorly conditioned problem will have a long, skinny contour like this. And if we, start over here, and if we do stochastic gradient descent, if we take long steps, we'll go right, the gradient will be really large in that direction because we're sort of far from the minimum along the direction across the ellipse. It'll be small in this direction because this ellipse is really shallow. And so we'll take a step that's like, really far across the ellipse, right? And now we're here and we want to take a step, the next step will be backward across the ellipse, right? And so that doesn't, that just bounces around a lot and doesn't get us anywhere. On the other hand, if we take let's start over here and take short steps, right? Well, so that's good, right? We're not going to jump back and forth, but we're not going to make much progress either, right? And so with a poorly conditioned problem, there's no good way to set the learning rate. What happens is just, if you set the learning rate too large, you're going to bounce back and forth across the narrow dimensions of your contours. And if you set it too small, you won't bounce back and forth, but you won't make progress either. And there's no way, because these dimensions are on such different scales, there's no way to set a learning rate that works for both. And so I described this for plain old gradient descent, but the same is true for stochastic gradient descent, just that you add, in stochastic gradient descent, it's going to be a noisy step along the gradient instead of an exact step. And so somebody is asking, is there a quantitative measure of a well-conditioned loss function? And in fact, that is exactly what we're going to talk about next. The quantitative measure is called the condition number. So we can define a condition number first for a quadratic loss function. So here's our quadratic loss function. The loss is 1/2 W transpose HW, where H is a, let's say we're minimizing it, so H is a convex up quadratic, meaning a positive definite matrix. All right, and so that's why I mentioned the tools for sketching a quadratic. We can use those tools to tell how well conditioned our problem is. So we factor H according to the singular value decomposition, call the factors U, S, U transpose. And if all of the diagonal elements of S are equal to 1, that means that our contours are completely circular. If they're all or I mean, not just equal to 1, if they're all the same, our contours are exactly circular. And if they're all approximately the same, our contours are nearly circular, or spherical in more than, in higher dimensions, hyperspherical, whatever you want to call it. But if the diagonal elements of S differ a lot, that means that there are some directions in which the contours are much longer than other directions. And so we can define the condition number to be the ratio of the largest and smallest diagonal elements of S, right? That's sort of the worst case difference between directions, and that's what's going to govern the speed of convergence of gradient descent. We want to set the learning rate small to handle narrow contours and large to handle stretched out directions of the contours, and the ratio between the two of them tells how much of a conflict there is between that. So that's for a quadratic loss function. With a non-quadratic loss function, if it's smooth, we can make a second order Taylor expansion around the local minimum, for example. And the contours of that quadratic function, the second order Taylor expansion, are going to be approximately the same as the contours of our loss function, at least in the neighborhood of that minimum. And so what we'll do is we'll take this second derivative matrix, H, from our Taylor expansion, and we'll apply this exact same set of tools. We'll factor it, US, U transpose, and we'll look at the diagonal elements of S, and if the ratio is large between the largest and smallest, it's a poorly conditioned problem, and if the ratio is close to 1, it's a well-conditioned problem. All right, so there's some more questions on Piazza now. Right, so somebody is asking about if there's no good way to set your learning rate in a poorly conditioned problem, can we do something, right? And so they suggest, for example, making your learning rate change over time. In fact, changing your learning rate over time isn't going to help. In a really poorly conditioned problem, you'll still get slow convergence of gradient descent or SGD. But there are things that you can do, and they are what's described in the next paragraph of the notes, preconditioning. And so we'll get to that after we get to, there's a couple of other questions up. So the first question is just a question about notation. So in a Gaussian graphical model, is the precision matrix a matrix of ones and zeros? No. The precision matrix has a specified pattern of entries that have to be 0, but the non-zero entries can be anything, anything they want, subject to the matrix being positive definite. So you can get a binary matrix that tells you the sparsity pattern, and that would be all ones and zeros, but the actual precision matrix is going to have arbitrary real numbers in the non-zero entries. Let's see. Is the learning rate the only factor that influences whether we make progress? Well, the condition number influences whether we make progress, and together with that, the learning rate influences whether we make progress. Those two factors together are enough to tell you a lot about how well stochastic gradient descent will work on a given problem. Obviously, in a given loss function, there's a ton of details that influence exactly what's going to happen. But for a sort of qualitative overall picture, if you tell me the condition number of your loss function and whether how high you're setting your learning rate compared to the scale of the problem, that's enough to tell you whether SGD is going, how SGD is going to behave. Is it going to bounce around or make slow progress? Or is it going to, sort of trade off as well as possible between those factors, even though, in a poorly conditioned problem, we're never going to have really fast convergence. All right. Okay, so all right, so let's go back to the notes. So let's see. I want to just say briefly what preconditioning is. So if you have a poorly conditioned problem, you would like to make it better conditioned so that stochastic gradient descent works faster. One way to do that is to do a change of variables, right? So you could think of, in a purely quadratic problem, if you have an ellipse as your contours, you can do a change of variables that turns that ellipse into a circle. And then you would have a perfectly conditioned problem, and gradient descent would work really quickly. Now, A, your problem is typically not going to be quadratic, and B, you're not going to know the right transformation ahead of time necessarily. But what we'll talk about next time we cover, next time we come back to these notes, is to talk a little bit about what would the optimal transformation be and what can we do instead given that we don't know the optimal transformation. And I think that actually makes a pretty good place to stop. So yeah, so my office hours start now. Keep asking questions on Piazza, and we'll continue to talk about preconditioning and the rest of the lecture notes when we return on Wednesday.